Okay, got it. Okay, so should I just launch into it then?
Yeah, go ahead.
All right. Good morning, everyone, for you. Well, maybe good afternoon or good evening for the people who are watching remotely. As I mentioned just a second ago, my name is Hergent. I'm a low energy nuclear structure theorist. I work at the Facility for Isotope Beams at MSU. And I was asked to give sort of an introductory talk walking from low energy QCD to nuclear structure. So you may notice I changed the title a little bit. The original title in the program said something about effective field theory. Well, I'm not an effective field theory person per se. I'm more a consumer of effective field theory interactions. So I'm going to leave the EFT expertise for the people, some of the people who are in the audience right there, for instance, Sebastian. And I put him on the spot for that. Okay, so to kind of start our little walk, I just first wanted to show you this slice of propaganda that kind of illustrates the progress that ab initio low energy nuclear structure has made over the past decade plus. So you can see here the chart of nuclides. And we have actually managed to extend our methods to the point where we can reach a great number of nuclei, or pretty much cover the chart, maybe up to the iron or nickel region. And then there's like specific regions, mostly around semi-magic nuclei, where we can actually go heavier. And if you look far up there, just last year, there was the first publication of a result for the neutron spin in lead-208 from ab initio coupled cluster and in medium SRG calculations. And I expect that Gaute will probably talk about that later this week. So the roadmap for how we can get from low energy QCD to nuclear structure has a couple of stations along the way that I just want to illustrate here. And the first of these is chiral effective field theory. So we're not working directly with quarks and gluons. That would be kind of nightmarish, just in terms of the number of degrees of freedom that you would have to handle. But instead, we work with pions and nucleons as our degrees of freedom. And then the interactions that we get from there may still not be so great for use in nuclear many-body calculations. But then effective field theories go hand in hand with renormalization group methods. So we will use those to kind of pre-process the Hamiltonians and make them a bit more amenable to solution with the methods that we have. And then those methods are kind of the last station in the road. So tools that we use to solve the Schrödinger equation in a systematic fashion, and then generate predictions for nuclear structure. Maybe eventually then also nuclear reactions as we try to create a bridge there. So I mentioned chiral EFT as a low energy effective field theory for QCD. So it encodes the chiral symmetry of low energy QCD. And the feature that gives it kind of an advantage over more empirical models is that you obtain a systematic power counting, an organization scheme for the theory that tells you how important certain contributions are, in particular, how important 2 nucleons, 3 nucleon, 4 nucleon forces, etc. might be in your framework. I will get back to that in a little bit. Then we are going to use RG methods. In our case, this is primarily the similarity renormalization group, so a unitary kind of transformation that you can use to systematically dial the resolution scales or the cutoffs of your theory. But there is a trade-off. So as I said, to motivate this, we want to actually make calculations, many-body calculations easier, converge faster. But then there is a trade-off that the RG is done in an A-body system and will in principle then induce new many-body forces. So it reshuffles contributions between 2, 3, and maybe higher body terms. And then last but not least, there's the ab initio many-body method, where the definition of ab initio to me means that we have an approach that solves the Schrödinger equations with approximations that I can systematically improve upon so that I can converge to the exact result. And while doing so, of course, if I have a systematic convergence, I should be able to quantify the uncertainties that I have because of using a finite order truncation in some sort. So that brings me towards mentioning these sources of uncertainties. So in chiral EFT, there are a bunch of them. So there's the selection of degrees of freedom. So we want to include virtual delta degrees of freedom or not. There's a choice of regulator that in principle should not matter if your EFT works properly. There are, of course, truncation errors because you're not going to implement your EFT to all orders. And then usually these EFTs have low energy constants that need to be fit to experimental data. Experimental data comes with uncertainties and they should be propagated to the final results of your calculations. In the RG approaches, like in any RG approach, really, you try to pick a basis of operators that is as complete as possible so that it can actually capture the RG evolution of your theory properly. And then to the extent that you fail to do that, you may incur truncation errors, as I just mentioned earlier. And then when we're doing many-body calculations, of course, we have to select model spaces. We may be working at some finite orders. We may impose symmetry restrictions on our model spaces. And then especially for exotic nuclei or like highly excited states, we really should worry about what happens when we couple our system to the continuum. Okay, then looking at the first stage of the station in yet greater detail, so you may notice I'm kind of increasing the resolution scale from slide to slide. Now we're going to delve a little bit into chiral effective field theory. And I just wanted to check, can you see my cursor moving on screen or?
Yes.
Yeah, okay. So chiral effective field theory, as I said, is like a particular low energy EFT of QCD. The degrees of freedom it uses are nucleons, which are the solid lines in these diagrams here. And then the nucleons interact via pion exchange, which is indicated by the dashed lines. And there are contact interactions like in any EFT, which encode all the short distance physics or high momentum physics that you're not explicitly resolving with these kinds of diagrammatics here. And as you can see, we can organize the diagrams of specific processes in powers of some momentum scale over the breakdown scale of the theory, which is like typically associated with the first degree of freedom that you don't include. So that would be like the rho meson mass, 700 MeV or so. There are now sophisticated Bayesian analyses of how the chiral EFT actually performs that suggests that the breakdown scale is a bit lower than that, so maybe 500 MeV. But then we have these powers of this ratio of momenta over the breakdown scale as an organizational scheme. So we can have a leading order, next to leading order, next to leading order, and next to leading order. And some people nowadays even have N4LO interactions. But then also what you see is what's nice about this framework is that it explains why 3 nucleon forces and then even higher nucleon forces are actually systematically suppressed compared to the 2 nucleon sector. Although there are still open questions about the power counting scheme and this framework in general that may suggest that maybe some of these parts of this interaction may have to be promoted, et cetera, et cetera. As I said, there are low energy constants that appear in this theory. So it's primarily these vertices, which you may notice are not all of the same size and shape. So some of these low energy constants we can determine from pion nucleon scattering, and this can be done very accurately. Then there are others that purely involve nucleonic degrees of freedom, and these you would normally fit to nucleon-nucleon scattering data. Or then in the case of this 3 nucleon contact here, you need some information about the 3 nucleon system. And ideally, well, one strategy, if you want, would be to completely fix these LECs in the lightest possible systems, and then to have like maximum predictive power towards all the heavier nuclei or observables in heavier nuclei and maybe infinite matter. However, there are some tensions there between if you try to do that, and some of the folks, including some people in the room, have proposed that maybe we should incorporate some data of infinite matter or slightly heavier nuclei into the fits of these nucleon low energy constants as we construct interactions. And then, since we're working in a field theory framework with a field theory Lagrangian to start with, we are actually able to gauge this Lagrangian and then in this way obtain the coupling to the electroweak sector, for instance. And there are then relations between the low energy constants that appear in the nuclear force to the low energies that may appear in the electroweak transition operators. So there are consistency conditions in some sense. So here's a snapshot of papers that discuss interactions that just came out in the last 5 years or so, a little bit more than 5 years. You see that in some sense, we are not having what we quite would like in an EFT, where you would say, okay, in principle, all EFT schemes should be equivalent. If the EFT is well constructed and well understood, everyone should be able to work in their appropriate scheme, and then they should be able to translate their results in such a way that they are consistent within uncertainties with the results that someone making a different choice for their schemes will obtain. And we're not quite there yet. So there are still some features of these chiral EFTs that are not fully understood. And as a result, there has been a little bit of what I would call skirmification, without wanting to insult people who like skirm functionals or Goni functionals. That has happened in these last 5 to 10 years, maybe, where there's been a variety of families of chiral interactions that have sprung up. And some of them work better than the others. And because of that, they kind of get preferred in applications. And this is, of course, not entirely satisfactory, because we would want the EFT to work, and we would want to have this comparability, as I said, where people in different schemes agree with what the other group could in principle produce within uncertainties. So there are, as I said, a variety of forces available. So you can check out some of these recent reviews in this Frontiers of Physics volume that came out in 2020. These are specifically then making choices about the regulators that are used in chiral EFT, which may be driven by the needs of particular many-body methods. I already indicated some people would like to include virtual delta isobars, so intermediate deltas as degrees of freedom, which will cause some reorganization of the power counting, of course. And then there have been now more statistically sound investigations of how these interactions are fit that have found that we maybe have to pay more attention to correlations between LECs as well as observables in the construction of these interactions, and then this can have an impact on the predictions that are made. And I just list some of the papers discussing that right here. And I mentioned before that there are some tensions that are revealed in LEC fits between forces that are fit to light systems only and forces that are maybe taking infinite matter or some medium mass nuclei data into account. I expect you will hear a little bit more about that in the talk by Maria Pierulli tomorrow. So I want to leave it at that for now. And I want to move on to discussing renormalization groups, or the similarity RG in particular. And again, here are some references. So you notice they are maybe not quite so new anymore. And that is just the reason for that is really that the SRG or SRG type methods are now pretty much part of the everyday toolkit of the nuclear structure community. Now, the basic idea of the similarity RG is that we want to perform a unitary transformation of the Hamiltonian. Unitary so that we preserve the spectrum and observables, of course, and we want to kind of transform Hamiltonian matrices or Hamiltonian operators in a way that makes them easier to handle in a particular many-body basis that I would call uncorrelated. This is code for saying I want to make my calculations simpler in some sense. Now, continuous unitary transformations we can write in the following way. So this is just a Hamiltonian that depends on some continuous parameter S that we call the flow parameter. And to implement those, it's actually convenient to take a derivative to derive flow equations. They look a lot like Heisenberg equations of motion right here, where this object eta is quite generally related to the unitary transformation like this. So you notice it's anti-Hermitian. And well, if you think back to how you implement unitary transformations, you may recognize that this can be understood as the generator of this unitary transformation. So that's what we call it. Eta is the generator. And we have actually quite a bit of freedom to construct eta in such a way that it achieves a desired behavior. For instance, we can split our Hamiltonian into two pieces. For instance, a diagonal part and an off-diagonal part, if you're just thinking of this in terms of matrices, and then set up the generator to be a commutator of these diagonal and off-diagonal parts. And then as you evolve, you would eliminate all non-diagonal parts of the matrix and you diagonalize the Hamiltonian matrix in the process. So I would say it's the world's most inefficient way of solving the eigenvalue problem for a Hamiltonian matrix. But this is, of course, not necessarily how we're using it, and I'm going to come back to that in a second. But then the nice feature, as I said, is we have this degree of we have this freedom to construct eta. And since it's a unitary transformation, we know in principle how to consistently evolve all observables of interest, which is not always so easy in other RG approaches, right? Where you need to maybe construct specific evolution equations in kind of non-trivial ways. So to illustrate how that SRG works, and I apologize to the nuclear people, you've seen this millions of times by now, but maybe the people from heavy ion or high energy physics haven't. So what I'm showing here is like 3D plots of the deuteron partial waves of the nucleon-nucleon interaction. This particular nucleon-nucleon interaction from NTEM and Mach lights or chiral N3LO force. This is given in relative momentum states. And then in the lower right corner, I'm plotting the deuteron wave function in relative coordinates that you obtain from solving the Schrödinger equation with this potential, which just shows that, well, you have S-wave and D-wave components, and there's this kind of suppression of the wave function at short relative distances, which comes naively from the repulsive core of the interaction if you apply a local picture of your interaction right there. Then we use this generator that consists of the kinetic energy, the relative kinetic energy, so it should drive this momentum space, these momentum space matrix elements towards diagonality in momentum space. Now we can look what happens as we evolve with the flow equation, and you can see that these off-diagonal pieces in these matrix elements become strongly suppressed, so the strength is swept towards the diagonal. This low momentum sector becomes more attractive as a consequence. You may have also noticed, whoops, going back a bit too far, that this coupled partial wave here, which is responsible for the SD wave mixing, is also kind of folded in on itself. So this interaction, this coupling interaction becomes weaker. And then you can directly trace the effects of that in this cartoon for the deuteron wave function. So you see that in the S wave, this short range correlation hole is pretty much completely eliminated, so that the S wave wave function looks like a simple Gaussian now. And you also notice that the D wave component has been suppressed as a whole. It's not completely eliminated. Need some of it. We need to break this particular symmetry. We need to have a quadrupole moment that needs to be preserved under unitary transformations, so it doesn't go completely away, but it's significantly weakened in the process. Now, this is great. I mean, we would have the ability to describe correlated nucleons with simple Gaussian states. I mean, sounds phenomenal in principle, right? But I mentioned already before that the SRG is really a unitary transformation in A-body space. So as we take steps of this flow equation, we are actually inducing higher body forces. So what I showed you before was just the projection of this evolution into the two-body space, where it is, of course, supposed to be unitary for two-body observables. But if you use this interaction and you did many-body calculations, you would see that you are not preserving the eigenvalues of the many-body Hamiltonian, because you're shifting strength from the two-body sector to the three-body sector and higher, or rather these sectors talk to each other. And this is illustrated schematically here just in second quantized language. So if you evaluate these commutators right here, like a simple one-body with a two-body will create a two-body operator, and then a two-body commutator of a two-body operator with a two-body operator generates a three-body already in the first integration step. And as you take more and more integration steps, now you have to evaluate commutators of three-body with three-body operators, which goes up to five-body, etc., etc. So these induced forces are there, and they are, of course, in principle, a problem. No one wants to handle them. No one in their sane mind, I should say. So we truncate them off, which in principle leads to a violation of the unitarity. And that needs to be quantified and needs to be tracked and quantified, ideally. The state of the art is that nowadays evolutions are done in three-body space, so which I want to say captures the bulk of the unitarity, and then induced four and higher many-body forces are truncated. What we do have, though, is that we have this dependence on the SLG flow parameter, which we can actually use as a diagnostic to probe how invariant the expectation values are in a completely exact calculation. So if you can solve the Schrödinger equation exactly, doing this transformation should preserve all eigenvalues. And if you see some variation in the eigenvalues, then this gives you a measure of how much you violate unitarity in the process. Okay, so now we're going to do a quick speed run through ab initio many-body methods. And as I said, you will hear more about some of them later this week from Thomas and Gaute and Thomas, because I haven't mentioned Thomas yet. So I want to say there are like three main paradigms for constructing ab initio many-body methods. First of those would be coordinate space, to work directly in coordinate space. And the example that's illustrated in this little cartoon to the right here would be a lattice EFT calculation, for instance. So I stole this figure from one of Dean's talks. Quantum Monte Carlo in principle is very similar, except that it makes the spatial variable continuous. So this is a bit harder to illustrate. I didn't have a nice cartoon for that. Then there's a very large category of methods which work in configuration spaces of specific many-body wave functions. And typically they do so by using an organization in terms of particle hole expansions. So what I mean by that is kind of sketched to the right here. You follow your essential many-body intro to many-body quantum mechanics principle. You take the simplest many-body state that you can build for fermions, which is a Slater determinant. You populate all the levels in your single particle space up to the Fermi energy, and then you can actually build particle hole excitations on top of this state. One particle one hole, two particle two hole, by just promoting particles from below the Fermi surface to levels that were previously unoccupied above the Fermi surface. And then the methods that you could then categorize this way would be many-body perturbation theory to all kinds of orders, because this essentially probes the coupling of the ground state to these kinds of excitations, and it derives corrections to observables that way. There are configuration interaction approaches which essentially construct these many-body bases of such states and then perform an exact diagonalization. So if you do that with keeping all nucleons as active degrees of freedom, you obtain what we in the low energy nuclear structure community call no core configuration interaction, or the shell model, or the no core shell model specifically. Then there's coupled clusters, so you'll certainly hear more about that from Thomas and Gaute. And there's the in medium similarity RG, which is a flavor of RG that kind of builds on the ideas that I mentioned previously, just for processing the Hamiltonian, and I'll explain a bit more what's up with that method a little bit later. I should say that when you build your many-body bases like that, you do not have to keep all degrees of freedom active. You can actually freeze some parts of your wave functions to introduce a core. Hence, then there would be shell model with a core instead of a no-core shell model. And that essentially just corresponds to selecting like an active space or a valence space and only treating excitations within this active or valence space explicitly. So we like to call it a valence space in nuclear structure. You may have heard the terminology active space if you've listened to talks from condensed matter or quantum chemistry, but the idea is very much the same. And then maybe more recently, or well, not so recently, if you think of it in terms of the EDF, the density functional theory context, there is what I would call maybe a mixture of these approaches where you're doing some kind of geometric expansion. So you're building configuration spaces of many-body states by essentially taking symmetries of the Hamiltonian, breaking them, creating then a basis of symmetry broken states, and then mixing them together in such a way that the symmetries will be restored, and you have a good handle of these specific correlations that you're going to capture very efficiently by allowing deformation. And methods of that type would, for instance, be then deformed Hartree-Fock or Hartree-Fock-Bogol-Lyubov for open shell nuclei with subsequent projection on particle number and angular momentum. Then taking that to the next level and allowing more configuration mixing, you get the projected generator coordinate method. So there have been talks about that in this program before, and you will hear more about that from Jean-Paul Lebrun on Friday, I expect. And then there is more recently also a symmetry adapted no-core shell model, which does not work just in this particle hole expansion basis, but instead uses the so-called symplectic group of the many-body space, which consists essentially of whose irreducible representation essentially correspond to particular nuclear shapes. But then you perform a diagonalization in a model space that's constructed across according to the symplectic group IREPS, and you perform the diagonalization in that. So it's more systematic in a way than how these deformed HFB and PGCM methods tend to work. And the nice feature of it is you're never really breaking the symmetry when you're doing that, which means then that you don't really have to worry about projections or as in the deformed HFB or GCM. So I indicated the talks that will follow up more on this week, and I want to, don't quite want to talk about the in medium SRG yet. I just wanted to show this particular slide, this particular figure that shows what happens if you take a variety of many-body approaches, and arguably most of them use this particle hole expansion scheme, but there's lattice EFT in here, and you use the same or at least consistent interactions, because lattice EFT deals with Lagrangians, not Hamiltonians, and you try to describe the same nuclei. Then within the scales shown here, which admittedly cover a significant range, you actually are able to achieve consistent results. So you're comparing apples to apples in some sense, right? Which is not really the case in most of the time when you're dealing with more empirical models, where you're baking in particular assumptions about the framework that you want to use your particular tuned interaction in. So this is the huge benefit of ab initio calculations. If people agree on the same inputs, and they can solve the many-body Schrödinger equation with certain truncations, then you should be able to compare results again. And in this way, then end up with theoretical error bars. Okay, so now, as promised or threatened, I'm going to talk a little bit about the in-medium similarity RG as a particular flavor of RG method, which still has a lot of concepts that are shared with these other approaches, so I can touch upon those within the context of my little corner of nuclear structure theory. And the problem that we're trying to tackle there is to avoid the large-scale, the exponential cost of large-scale diagonalization approaches like the no-core shell model. So what's shown here is a graph of the matrix dimension as like a basis parameter in the no-core shell model. So this characterizes the excitation levels of the basis states that you're including. To the right, it shows the number of non-zero matrix elements as a function of the matrix dimension. if you include two-body interactions and three-body interactions in your many-body Hamiltonian matrix, and the nuclei you're looking at are still very light, just p shell and then the lower SD shell, and you see that, well, the matrix dimensions quickly reach 1 billion or 10 billion, and the number of non-zero matrix elements, although the matrix is extremely sparse, right? It's just 10 to the 12 matrix elements out of 10 to the 20 or more. Still, it requires so much storage that you would need an entire supercomputer just to hold the Hamiltonian in memory, if you're not clever about it, of course. So this is a huge problem. There's this exponential growth that one can try to mitigate by using, for instance, importance truncations ideas, like you select a certain basis status based on some measure on how you expect them to contribute to ground state energies, for instance. But the problem is that even these kind of importance truncation techniques cannot really fully compensate this exponential model space growth as you try to increase the mass of your nuclei and you want to go to heavier nuclei, which, I mean, as I said, it's really the bulk of the nuclear mass chart that you're not able to approach in this exact diagonalization method here. Now, we talked about how we can use SRGs to transform matrices, but we can, of course, use them to transform the operators themselves without necessarily building matrix representations of the Hamiltonian. And this is going to be like the central idea that we're going to pursue. So let's just imagine we have a Hamiltonian with a two-body interaction, and let's consider how this Hamiltonian would like schematically as a many-body matrix. So we're picking again our reference Slater determinant right here, which is this little corner of this matrix cartoon. So this would be a one-dimensional space. And then we build all possible particle hole excitations, one particle, one hole. This is this block of the matrix. So this is larger than one-dimensional, of course. Then there's two particle, two hole excitations. If we only have two-body interactions, we can't excite three particle, three hole excitation of this reference Slater determinant at once. But as I said, I mean, we have three-body forces in principle. I just left them out of the cartoon just to simplify things a little bit. Now, the basis, by organizing in terms of these particle hole excitations, is amenable to a technique that we call normal ordering. So in principle, you build in some information about the particular nucleus that you're trying to describe by selecting this reference Slater determinant, which is some approximation to a many-body state of that nucleus, right? It will be having the same number of nucleons, the same number of protons and neutrons. And if you optimize it, for instance, variationally with the Hartree-Fock method, you have at least a reasonable guess, perhaps, what the ground state of that nucleus could be. And then in some sense, by building excitations on top of that ground state, you're folding in information about the characteristic energy scales of the nucleus into your basis, and you organize it in a particular way. That basis, of course, is still going to be complete. I mean, if you could go to a particle, a hole excitations, you're not truncating your Hilbert space in any way. So we have this matrix, and now we want to think about what we could do instead of brute force diagonalization. Namely, if we could perform a unitary transformation in a way that decoupled this sector, this one-dimensional block, from the rest of the spectrum, so from all of the excitations here, then we would by construction extract an eigenstate of the Hamiltonian in doing so. And we would map this reference state onto an exact eigenstate of the Hamiltonian matrix. So we have the eigenvalue and the exact eigenstate. And we do that by using a flow equation and directly working with the operators. So we do not have to spend this exponential effort of building these huge matrices. We directly work with the operators themselves and their coupling constants, which makes this a polynomially scaling method. I should say, though, as I say coupling constants, we're not working in the space of 20 chiral LECs. So these are really like n to the fourth matrix elements or coupling constants of these operators that we need to handle, where n is the single particle size, single particle basis size, which can be on the order of 100 to 1,000 or maybe a few thousand. So this is polynomial, but it can still get very computationally expensive very quickly. And then the generator, as in the initial example that I mentioned, we're going to define as this commutator of diagonal and off-diagonal pieces, where diagonal really now just means the part of the operator that I want to keep, and off-diagonal is the part of the operator that I want to get rid of, because we're not dealing strictly with matrices anymore and diagonal parts of a matrix. We're dealing with this in an implicit sense. And then I want to define the off-diagonal parts of the Hamiltonian to consist of these particular operators that couple the reference state to one particle, one hole, and two particle, two hole excitations. I can evaluate that. I can define my Hamiltonian in this way. And then when I do that, well, there's particular two-body operators that are responsible for this coupling. Then I can essentially truncate all my operators at the two-body level, which is an approximation, because as before, if we take integration steps, we induce higher body terms that we're not wanting to treat explicitly right now, but we still stick with the polynomial cost because we never actually need to build this exponentially large matrix in the first place. So let's see how that would work. And what I'm showing here is the calcium-40 ground state energy. It's just with a softened SRG softened chiral interaction. So that's why calcium is horribly overbound right here. The blue curve is just, I would say, the Hartree-Fock energy. So a simple mean field energy that you get with a Hamiltonian as it evolves in S in this flow parameter. And what's shown in red is like the correction from second order many-body perturbation theory that we would be picking up if we did second order MBPT with the evolving Hamiltonian. To the right, I just show a particular partial wave in the particle hole basis, or sorry, in the certain segment of the coupling constants of the Hamiltonian operator. And I highlight those that are essentially the off-diagonal pieces that I identified in the previous slide. And now I can start the evolution, which is shown by this red, gray bar that is moving through the left plot. And you can see as I evolve with the in-medium SRG, what happens is that these couplings that are defined to be off-diagonal are driven to zero. And then all the energy that I would have gained from perturbation theory has been summed into the operator itself. So if I take this evolved Hamiltonian and I perform a simple mean field calculation with it, I essentially get the same result as doing like a higher order correlation corrected calculation with this Hamiltonian. So this is pretty neat. So we're reshuffling correlations into the Hamiltonian. And just to illustrate that a bit more, we can think of writing down the stationary Schrödinger equation and then inserting the unitary transformation operators right here. So what happens is that normally we have to solve for the eigenstate psi n and for the eigenvalue En. But when we do this unitary transformation, essentially what we get away with, which is hopefully less work, is to solve for this unitarily transformed eigenstate. And then we make particular ansätze for that unitarily transformed eigenstate. For instance, as in the example I showed here, we make the ansatz that this is just a simple Slater determinant. And interestingly, you may recognize that this is almost like a constructive method for achieving what density functionals claim to be doing, which is that all the correlations are built into the density functional, and then you use a theoretical method that very much looks like a mean field method to obtain your ground state energies and other observables. Of course, this effective Hamiltonian arguably would be something like a density matrix functional, and the density matrix dependence that is coming from this reference state choice is highly non-trivial and very, very implicit. So I'm not claiming that we can use this anytime soon to derive energy density functionals that have like a proper ab initio background. It at least conceptually, though, would open the doors towards doing something like that. Okay, so in principle, as I just said, we make this ansatz for the unitary transformed eigenstate, and we can pick ansätze for that have no correlations built in whatsoever. That would be what I call the standard IMSRG approach here. So we build correlations on top of a Slater determinant, which is an independent particle state, but then it means that the IMSRG has to describe all the correlations in the system somehow and has to shuffle them into the Hamiltonian. So that would be these kind of pairwise correlations, triples-like correlation, quadruple-like correlation, quintuples, et cetera, And as you can see from the labeling up top here, IMSRG2 means we're including only two-body operators in our flow equations. IMSRG3 means we're truncating after the three-body level, truncating after the four-body level, truncating after the five-body level. So this means we would have to keep 3, 4, 5-body operators to treat these kinds of correlations with the nuclei, which quickly grows out of hand because, yes, it's still polynomial effort, but then the polynomial would be something like single particle basis size to the power 15. And if your n is your single particle basis size is 1,000, that quickly becomes infeasible with the largest computers that we have as well. And just to say that this is not a merely academic point, well, these kind of high body collective correlations is exactly what drives intrinsic deformation in nuclei, which is, after all, like a theme of this workshop or of a theme of this program, right? Dealing with nuclear shapes. You can imagine that in this naive picture, you would have built like a spherical Slater determinant, and then if you want to get these kind of prolate and oblate shapes, you need to move 5, 6, 10 nucleons around at once, which in IMSRG language would require IMSRG 10. So that's a pretty horrible idea then, to try and capture these correlations that way. Instead, what we can do, well, we just said we use the Slater determinant as an ansatz for a unitarily transformed eigenstate. But who says that we only can use Slater determinants for that? Why not try and use some correlated reference states that have some of these collective correlation baked in, and then use IMSRG to capture the few particle high energy correlation, dynamic correlation, sometimes that's what they are called in the chemistry literature, by doing the in medium SRG procedure on top of this correlated reference state, this collectively correlated reference state. So we're trying to get the best of both worlds, one approach that covers both kinds of expansions in a way. You may have also heard this referred to as like vertical and horizontal expansions earlier in the program, where the horizontal expansion is kind of the collective high particle, low energy correlations, and then the vertical is like the few particle high energy type correlation. So if we adopt that idea, then we can actually set up a host of IMSRG improved many-body methods, where we use a particular scheme to define a reference state, and that can be either a mean field or explicitly correlated. Then we perform an IMSRG evolution to construct RG improved operators. And then we take those operators and perform a many-body calculation again to extract wave functions and observables that we like. In principle, then you could even add consistencies. So you get wave functions out of here, and then you could use those as reference states in the IMSRG procedure if necessary. Now, there have been quite a few of these kind of IMSRG improved methods developed in the past 10 years or so. And in fact, the standard IMSRG from that perspective, you could view as an in-medium Hartree-Fock approach. And then there's an in-medium projected HFB, which is what was responsible for the no-core in-medium SRG results for oxygens that I showed on this previous comparison slide with other methods. There's the valence space in medium SRG, which essentially derives interactions for the traditional nuclear shell model. There's an in-medium no-core shell model, and there's the in-medium generator coordinate method. And these, the in-medium GCM and the valence space IMSRG are the ones that I want to talk a bit more about in the following. So let's start with the valence space IMSRG. So as I said, this is deriving shell model interactions and operators, which then people who have been doing empirical shell model calculations can easily use in their codes. And what's shown here is just an overview of ground state energies for very light nuclei. Still, this is like carbon through oxygen. There's SD shell nuclei, sodium and calcium, and then there's nickel. And we're comparing many-body methods or results from many-body methods for the ground state energies of the valence space IMSRG, which still goes by its previous name under here. So it's the red results with other approaches like coupled cluster, self-consistent Green's function, or the no-core shell model, and essentially exact diagonalization. And we see that again on the energy scales right here. If we use the same Hamiltonians, we get consistent results. However, you also notice that, well, now in the medium mass region, this Hamiltonian clearly doesn't work that well because it predicts overbinding. But it's not a fault of the many-body methods, because all the many-body methods are consistent within their truncations now, I would say. It's really a problem with the interactions that we're exploring there. You notice that the valence space IMSRG, so the red symbols are maybe the most frequent ones here, and that is because the valence space IMSRG can easily access odd nuclei and excited state, which makes it pretty appealing for use, and it gives you access to the spectra and odd nuclei in a very, very easy way. So you can look at other quantities besides just ground state energies. And one very nice study that was done a couple of years ago, about 3-4 years ago by now, that involved coupled cluster and valence space IMSRG, was to look at a long-standing problem in beta decays and gamma-Teller decays. So let me explain this a bit. So there is the measured gamma-Teller strength on the vertical axis in these two graphs here for various nuclei. There's a theory prediction of the gamma-Teller strength of the gamma-Teller transition matrix element. And what had been found in empirical calculations, which are shown in orange here, is that if you do like simple shell model calculations, you always need to introduce like an empirical phenomenological quenching of the axial vector coupling GA, which is typically on the order of like 20 to 25% in these SD and PF shell nuclei. But then in green, we show what happens if you do valence space in medium SRG and you consistently renormalize the operator and also account for current corrections to the electroweak transition operator. So you build the transition operator according to EFT principles. And as you can see, it's not totally perfect yet because there are still truncations in the valence space IMSRG, but you essentially can explain away this empirical quenching. So this empirical quenching always mocked up the more microscopic correlations that you're now explicitly resolving in this valence space IMSRG approach. So if you properly work on the microscopic physics, you don't need any phenomenological fudge factors or quenching factors. So we understand what's going on.
Heiko.
Yeah.
So sorry, I was couldn't miss the part of your talk because I was in some doctor appointment. I have a question on this valence space SRG. You have a plot to show the idea where you have this valence space and then the rest, right? Like if you the horizontal and the vertical. My question is the immediate SRG itself evolved these two scales separately, or they are like added up afterwards? Like, is this consistently treated in the immediate evolution itself or not?
Well, yes, because you essentially can tell which orbitals are in the valence space and which are in the core. So then the whole point of the medium SRG procedure is to eliminate the coupling of the valence space to all the stuff that's not in the valence space. So you can precisely use it like that to construct. That's how these shell model interactions are constructed. So all the physics that is not covered by the valence space itself should be baked into the effective operators. Now that gets very tricky if you are actually in a situation where your nucleus wants to deform very, very heavily, right? So there's things like intruder phenomena, that's kind of just like the jargon word, where the notion that you can freeze a core and set that core apart from the valence space may not be such a good idea. And what's going to happen in that case is that probably the valence space evolution is going to blow up. So you're not going to be able to decouple that nicely. But there are ideas. I mean, I'll argue that there's many ways to build like hybrid paths where you maybe would kind of do like a projected calculation for the core, projected correlated calculation for the core that builds some deformation in, and then you define a valence space on top of that and do decoupling again. So maybe then that could cure the hypothetical blow up. So there's a lot of ideas that we have that we can try. We just need to actually get around trying them.
Okay. How do you decide the scale for which you throw away, like the
so in the valence space IMSRG, what you actually do, you want to completely decouple normally. So you really don't want to introduce an additional scale whereby stopping the evolution at a particular S, you want to evolve all the way to infinity. So you're really decoupled. So if you think of S as kind of like related to the excitation energies, you want to completely get rid of all the excitations of the stuff that you want to keep to the stuff that you don't want to keep, right? And so you want to completely eliminate that. And that's why you would want to evolve to infinity, so that these kind of excitations are completely taken out of consideration. Whether you can achieve that is a different question. Right.
Okay, thank you.
All right. So picking up from where I left off, so the valence space IMSRG worked pretty well then for this beta decay example. But then the beta decay example, of course, is something that involves transitions of single particles, right? What happens if we look at something else? For instance, like quadrupole transitions, so electromagnetic quadrupole transitions. So that's shown here for a bunch of nuclei. So on top, there's like the 2+ excitation energies for like the valence space IMSRG, and a no-core excited state method that I really don't want to go in a lot of detail on, other to say that it's kind of consistent with the valence space IMSRG, and the energies are not so terrible. But then if you look at the BE2 values, which are shown in the lower panel, they are significantly underestimated compared to experiment. And the issue there, but it's not all bad news though, because if you look at oxygen 22 itself, here the valence space actually just consists of neutrons. So naively, you would not even expect there to be a BE2 value in the first place, because the neutrons are uncharged. So the fact that this value is non-zero means that the IMSRG transformation has produced an induced neutron charge for you, which again, in an empirical approach, you usually have to mock up by introducing it by hand. It's not perfect though. So clearly we're missing correlations. And as I indicated before, well, the valence space picture is very much rooted in these particle hole type expansions, whereas we have strong static correlation that have something to do with nuclear shapes and deformation. And these are hard to capture in a particle hole expansion. So these are the ones that are missing here. And of course, the quadrupole transitions, these are closely associated with shape fluctuations, right? With deviations from the spherical shape. So to do better on that front, we actually combined the medium SRG with a generator coordinate method, which you may have heard about earlier in the program. I think Benjamin probably talked about that in his talks. So there you very much kind of, as I indicated before, take the idea that you're breaking symmetries of the Hamiltonian, you create deformed shapes, then you do configuration mixing of these shapes in such a way that you're restoring good angular momentum and particle number and other symmetries. And this gives you a very, very efficient way to capture these strong collective correlations that we have in nuclei. So what's shown here are RMS matter radii of magnesium isotopes, which are like an interesting chain of isotopes because there's the so-called island of inversion that happens here. There's an intruder state phenomenon that you really cannot describe well in the traditional shell model. What you get in the IMSRG in medium GCM, so this is still under its old name, you can actually get the trends of these RMS radii pretty well with the GCM method. You underpredict the radii by about 5–6%, but that is a feature of this particular chiral Hamiltonian that is used here. So it's known that it gives excellent binding energies, but the nuclei turn out a bit too small. So,
question.
Yep.
So I wonder if you in this GCM, right? Is this just the beta and gamma and those collective coordinate you're using?
In this case, it's actually just axial transfer. It's just axial degrees of freedom, so just beta. Yeah, but beta and gamma would be the generator coordinates that you use to characterize the basis configurations.
So that when Benjamin gave him his talk, right? In his approach, he starts from you know, the solution from mean field, which are fitted to the data. That is one of the limitation, like double counting, that he's worried about. But in your approach, there's no such issue, right? Or
there is
there's
no, and especially so. Essentially, we're working with him. We're feeding in medium SRG Hamiltonians into that pipeline. I'll have an example in 2 slides.
Okay. But only for small system, right? And so far.
Let me get there. Okay. So what's shown here then is the kind of the same observables as before, 2+ energies and BE2s. So we see that, well, actually just the GCM with the chiral interaction doesn't do all that badly on the 2+ energies, because this is very closely associated with collective correlations. In fact, the medium SRG kind of bumps up the 2+ energy in magnesium 30, which is, I believe we understand that. But then what happens here is that suddenly the BE2 values are almost spot on, which is actually one of Bob Ross's happy little accidents, I would say, because they are in a way too good to be true. Because we saw in the previous slide that the radii are actually underpredicted, and the quadrupole transition operator, of course, also has like an R² dependence in it. So you would expect the BE2s to be a little bit underpredicted as well, or 5% underpredicted or so, and not to be quite as good as they look right here. But you see, again, you get like the general trends correctly. And then the interesting bit is that if you analyze the renormalized operator, you actually see that the bulk of the renormalization in this IMGCM approach happens in the one-body part, so the one that you can control very well. And then two-body parts and higher body contributions are corrections on the orders of a few percent to that. So this is very different from what would be happening in the valence space IMSRG, where the bulk of the effect actually has to come from higher body induced contributions, which you then cannot capture very well, which is why you mess up the BE2 values of that. So this slide, I just flashed that just to illustrate, you can actually look at like non-observables like occupation numbers for the GCM state, so that always has to be done very carefully. But qualitatively, the picture that you get matches with what you could find in the shell model as well. So you have this kind of inversion of occupations, which would in standard shell model language correspond to intruder configurations. So in this slide, it's actually then what I just mentioned to Zhang Yong, is that we are feeding now these IMSRG Hamiltonians into projected GCM, and John Paul will talk about that more on Friday. So this shows like neon 20 binding energy as a function of the IMSRG evolution scale or evolution parameter S. And here's a bunch of results where the open triangle would be like a spherical restricted Hartree-Fock calculation. Then the solid triangle comes from allowing deformation, and you see that you gain energy in those cases. And then from the triangle to the circle, you perform configuration mixing in the projected GCM. And then from the circle to the red star, you actually do perturbation theory on top of the GCM with a novel method that the Saclay group has developed. And if you use the unevolved Hamiltonian, you actually see that to go from spherical to deformation, you pick up energy, to GCM, pick up a bit more energy, but then you're leaving out a lot of dynamical correlation, which you recover with this PGCM second order perturbation theory, like 40 MeV. Now, if you evolve the Hamiltonian, all this dynamical correlation gets shuffled into the Hamiltonian itself, and you see that the red arrows now shrink. So they become like not quite subleading, but they become suppressed compared to the corrections that you get from treating the geometric shapes of the nucleus. So that on the right, we show the corresponding excitation spectra, and you see that, well, there is some improvements, some things that get a little bit worse, but we know that because the states may not be rich enough, so we're not recovering all the dynamic correlations perfectly yet. And it's just to say that we also need to keep on working on the IMSRG truncations, but then this route of feeding in medium SRG Hamiltonians into these PGCM calculations is very, very promising going forward. So I'm going to skip over some of the other transitions and stuff, maybe continue that as my last bit, but Jang-Yong, go ahead, please.
Yeah, sorry for asking many questions, but for your if you go back to your energy gain for these different steps, so the first step is always almost the same, right? Going from restricted hydrophobic to unrestricted. Is this by design?
It's not by design. It just turns out to be the case.
Okay, but they are really not changing much.
Yeah.
Okay.
I mean, one can probably understand that in more detail, but to be honest, I haven't really thought hard about it. It's something to note. Maybe we can understand that in more detail. But yeah, that for me, like the striking bit of this is that the dynamic correlation really shrinks because you systematically build it into the Hamiltonian here. So it's the shrinking of the red section that excited me the most in this picture. Okay, so we did this for the neutrino double beta decay, yada yada yada. Don't want to go into detail. There's the references in here. We are actually computing neutrino double beta decay matrix elements in germanium and xenon now with this approach. The biggest hurdle used to be the input interactions, but as you may have heard about the fact that the Triumph group actually made a lot of progress in the handling of three-body forces. There's now some additional ideas from the Darmstadt group just from last year, from fall last year, that will help us overcome that hurdle, and then we should be able to really push past the tin xenon region then into the masses 150 to 200 or so. So the last thing I wanted to show here is that if you allow these kind of GCM reference states, you can actually use generator coordinates that allow you to describe clustering. So this is just illustrated in a very, very early stage here for beryllium 8, where you can see you can generate basis states with the double alpha cluster structure. And then we can do the IMSRG evolution, and we can do IMGCM and compare it with another flavor of in medium SRG enhanced many-body method, namely in medium no-core shell model. And we see that we actually get like consistent features in the spectra. So it's not all perfectly matching and not all perfectly understood. There's definitely a lot of more work to be done. But I just find it exciting that we are able to kind of identify particular geometric shapes, including the cluster structures here. Now, the challenge is that if you want to describe clustered states with a GCM, the GCM will become a very, very heavy calculation in itself. So the IMSRG evolution is actually not going to be driving the computational cost anymore in many of these examples. So looking ahead, and I'm going to go a bit quickly here. So clearly what we want out of this ab initio program is the ability to do like precision nuclear physics, where we want to be able to describe all the nuclear phenomena that can appear, including complex deformations like shape coexistence, clusterings, halos. So this is the stuff where there would be a lot of potential opportunities that we can explore together with the heavy ion community. Now, these kind of precision nuclear physics is very important for the fundamental symmetry program. So I mentioned briefly neutrinos double beta decay, but there's like precision beta decays that are needed as input for tests of the unitarity of the CKM and PNMS matrices that are very, very high interest to that community. There's the search for nuclear EDM, so where we need to compute shift moments, which is going to be something we're going to try in the next 5 years or so to go like to xenon 129, then mercury 199 and radium. And then a big thing that I sort of touched upon is the matter that we really want to be able to perform a systematic uncertainty quantification and sensitivity analysis. So ideally, we want to identify nuclear observables that can be strongly constraining on the nuclear forces. But there's my little corollary to that, that usually the quantities that are most constraining are also the ones that are most difficult to compute for us. So they will require lots of computing power, and there will be many steps in the calculation. Now, to kind of help set off those computational costs, we need surrogate models or emulators, or more generally think about model reduction, which has become a very active line of research in our community as well. And there's like a huge body of work out there in mathematics, applied mathematics, engineering. And I just wanted to flash that very nice result by Gaute and Andreas Ekström, where they did ground state calculations of oxygen-16 in coupled cluster and analyzed the impact of varying the LECs of the chiral Hamiltonian on the ground state energy observable. And this was made possible by the availability of surrogate models of like very cheap emulators. So they could run millions of calculations on a laptop essentially, instead of using HPC resources. So my group is working very, very hard on developing emulators for the IMSRG, which is a bit more challenging because of the way the problem is set up. And I just left some site references right here that you can check out on the web version of the slides. So then the grand horizon is kind of that we want to go to this predictive ab initio theory with systematic uncertainties and convergence to exact results. I hope I've convinced you that there's a clear route to go there from low energy QCD, kind of following like a tower of theories, and then pinning down the uncertainties as you go from step to step, even though a lot of work has to be done still to pin down those uncertainties, and that we're working very hard as a community to expand our capabilities and to compute more interesting observables. My personal ultimate dream is that we will eventually be at the point where community codes will be so performant and scalable that they can be used in day-to-day data analysis, or then in specific problems that demand high precision in leadership calculations on the largest machines that we have available to us. So there's a lot of people who have contributed to that. I want to thank them. And then if you pardon the plug, there is currently an open postdoctoral position in my group at EFRIB. And if you are aware of qualified candidates, please encourage them to apply. Review of applications has started, but it will continue until the position is actually filled. So the information is on the slide here. I'm going to go back to the thanks, and I thank you for your attention.
Thank you, Heiko, for a very nice talk. Are there questions? Yeah, hey, Gaute.
Hi, Heiko. Can you hear me?
Yes. Yes,
Okay,
Aldo.
great. Thank you for a nice talk. So I want to come back to the BOE2s you showed.
Yeah.
So the first case you showed the discrepancy for closed shell nuclei, spherical cases, right?
Yep. Well, I mean, there was, where is it?
Yeah.
Yeah.
So
I
these
mean,
are all spherical nuclei.
arguably, sulfur is kind of like a closed subshell. Right.
Right, but they all can all be treated within a spherical like fork reference kind of thing. So how would you? So then you showed the other case with magnesium, which obviously are deformed, where you can actually create a deformed reference either via GCM states. So in this case, you get a 2+ states that are too high, right? But you get
But it's really only in magnesium 30 though. Right. I mean, they're slightly too high in the heavier ones too, right? But it's yeah.
How do you understand that at the BU2 is not smaller than experiment?
So wait, so sorry. So what did you want me to compare it to?
You on top of experiment one, the 2+
Yes.
about half a MeV or so, or even more for
right. So I mean, if the 2+ went down, then you would expect the BE2s to go up further, right? So what I can say is then you would really need to look at the higher body induced contributions. Because again, as already I would say at this level, the fact that the BE2s agree very well with the experiments is an accident, because we know that the interaction makes the nuclei too small, right? So you would naively expect them to be suppressed by the higher 2+ energies, and more suppressed by the fact that the interaction actually makes the nuclei smaller than they should be. So the fact that they are on top here is probably then a truncation effect. So you really would want to look at like particular contractions of the, I mean, it's getting very technical, but particular contractions of the 2-body operator and the effects of like 3-body correlations in the reference states. So we have implemented them in the meantime since these calculations were done, but we have not gone back systematically to the magnesiums yet to see what the impact there would be.
How would this work for spherical nuclei?
I mean, in spherical nuclei, I would say it's more challenging to get the excited states right. So you know, it's typically if you have like, let's say, low-lying 0+ and stuff, then the structure of these states is more complicated than what you have in a deformed nucleus where you have like a nice rotor spectrum. And I think this is actually the reason why you're seeing that the in medium SRG evolution makes the 2+ energy worse. You're kind of optimizing too much to the ground state and not so much to the first excited 2+. Whereas when you're in the open shell, they are kind of mixed together a bit in the first place, because this is supposed to be deformed. So you're grabbing both of the states and you're dragging them down in energy the same way. So you're benefiting from the fact that the shapes are not so clean, or the states are not so cleanly separable anymore. This is something we've seen over and over. This also happens in Neon 20, by the way. So I expect that the excited states in spherical nuclei can be harder to do, because they might require higher body induced correlations or higher body correlation density matrices for the analysis.
The 2+ states are basically on top of the experiment and converge within the truncations. So, but then the BAB2s are obviously far away from it.
Only in oxygen though, right?
Well, we've done a couple cluster doubles and triples, and we see.
Right, but you have the triples, right? The triples reduces the energies, right, for you guys typically.
Yeah.
I mean, right.
But I would say that 2+ energy level is much more under control than the corresponding BOE2s.
Yeah.
That's I don't know. See how that scheme can be used for solving that problem that you use for the deformed cases.
Right, but I mean, well, the natural thing is you would go to I mean, you need to check what the induced contributions are and what the effects of the free body correlation densities of the correlated reference state are, right? So this is the generalization of saying I need to look at triples and maybe what happens beyond that in the open shell nuclei here.
Okay, there's a question, Jiang, go ahead.
So I will, in your summary slide, you mentioned the heavy ion, the challenge for heavy ion connection. So I wonder, these two comments, the issue with the scale and the scheme dependence, this, I guess this refer to the nuclear structure side of the difficulty, or this is all.
I mean, I may not know. I don't know enough about the heavy ion collision side to understand how you extract certain things. I mean, I know more recently there's like work that uses like ratios of I guess like flows that might eliminate some model dependencies in the extractions there, but in general, like coming from the RG side of nuclear structure, it's very important that one is very, very careful in how one interprets things that may not be observable, right? So if you can reduce everything to observable comparisons, then that is very clean. But as soon as you have some kind of non-observables like occupation numbers, wave functions, intrinsic shapes, at least in the low energy nuclear structure side, intrinsic shapes before projection or before restoration of the quantum numbers are not directly observables, right? And you can construct, or you can get the two values in principle, as you could maybe surmise from my walkthrough, in different ways. I mean, in principle, you could build them on a spherical nucleus as a 10 particle, 10 hole excitation. Right?
Mm-hmm.
Or you could build them by deforming and then getting some correlation on top of the deformation and mixing things together in a maybe more geometrically intuitive way. And both of these descriptions should, in principle, be able to give you the same results, or should converge to the same result for the observable. But how you interpret the intrinsic structure, or how you interpret the structure of the states along the way, it can be very, very different.
Yeah. So we had this discussion like 2 weeks ago, whether one calculate different quantity. Let's say if you can calculate 2-point correlation function, project out a two-point correlation function, which may be more directly related to the high energy. I don't know. I mean, it's probably something that needs more discussion. I have a further follow-up on this. For the ruthenium zirconium, the zirconium 96, for example, is mid-shell, but to me, it have a quite a large, let's say if you have a large beta 3, you can still see it's a fluctuation. But do you think in this immediate SRG, you can handle like you have a system with very large fluctuation, but it's not static, but still is quite large. Do you think you can, in your method, you can handle the zirconium 96 or ruthenium 96? Yeah.
So I mean, one of the so far we've done primarily nuclei that have like axial deformation. So this is the starting point, but the things are pretty well under control. I mean, where you only have to worry about some generator coordinates. So now we're going into more deformed shapes, like let's say in the work with the people from Saclay for neon, where you open up octopole degrees of freedom. And then for these neutrinos double beta decay candidates, we also need triaxial shapes, like germanium has shape coexistence of all kinds. So in principle, we are building the machinery to deal with the situations like that, where you have like, mixing fluctuations of spherical, prolate, oblate shapes, all of that kind of stuff. I think zirconium has shape coexistence. There's like another nucleus in the vicinity that's again is like molybdenum 100 for the fundamental symmetries program. That's of very high interest, and that has a very rich structure intrinsically that is dominated by like shape coexistence and stuff. So I think we will get those. The features that will then be even more hard to describe will be things like clustering. But I think as long as it's a blob that deforms, arguably, I think then we'll be fine. We'll get there within the next couple of years or so.
Mm-hmm.
Okay.
Thank you so much.
Yeah, thank you, Heiko. So I think we will take a break now and come back in 20 minutes. We'll have our second talk then. So Heiko, I don't know if you can come in the afternoon, but we'll have a discussion.